Hello students, we'll continue root stability criterion. Hurwitz criterion, special cases. Special cases of root array. The first element of any row of the roots array is 0. All the elements of any row of the roots array are 0. So special case 1, first element of any row of the roots array is 0. If any row of the roots array contains only the first element as 0 and at the least one of the remaining elements have non-zero value, then replace the first element with a small positive integer epsilon. And then continue the process of completing the roots table. Now find the number of sign changes in the first column of the roots table by substituting epsilon tends to 0. So now we'll take an example of this. Determine the stability of the closed loop transfer function T of s is equal to 10 divided by s to the power of 5 plus 2 s cube, s to the power of 4 plus 3 s cube plus 6 s square plus 5 s plus 3. So now s to the power of 5, if we take 1, 3, 5 and s to the power of 4 is 2, 6 and 3. So s to the power of 3, if we calculate to 2 into 3 minus 1 into 6 divided by 2. So we're getting it as 0. Second value we'll get it as 3.5. Now I'm replacing that 0 value by epsilon. So now continue the calculation part. So s to the power of cube column will be epsilon 3.5 and s square is 6 epsilon minus 7 divided by epsilon and 3, and s to the power of 1 is 42 epsilon minus 49 minus 6 epsilon square divided by 12 epsilon minus 14, and s naught is 3. For the epsilon tend to 0, there will be two sign changes. In the first column, as there are two roots of the characteristic equation in the right half of the S-plane, and hence the system is unstable. So we'll take next example. Determine the stability of the system with the characteristic equation. So the given equation is s to the power of 5 is 1, 2, 3. To the power of 4 is 1, 2, 5. So the s to the power of 3 row value will be 0 and minus 2. Now that 0 value should be replaced by epsilon and minus 2. Then epsilon into 2 minus 1 into minus 2 divided by epsilon. So 2 epsilon plus 2 divided by epsilon and 5. So s to the power of 1 is minus 5 epsilon square plus 4 epsilon plus 4 divided by 2 epsilon plus 2 and 5. S naught is 5. As epsilon tends to 0, there will be two sign changes in the first column. Hence there are two roots of the characteristic equation in the right half of the S-plane. So the system is unstable. Alternate method. Transform the characteristic equation by replacing s by 1 by z and apply the root test. Let the equation be. So given equation, so replacing all s terms by 1 by z. So 1 by z power 5, 1 by z to the power of 4 plus 2, 1 by z to the power of cube plus 2 into 1 by z square plus 3 into 1 by z plus 5. So if you simplify that, we'll get the equation as 5z cube plus 3z to the power of 4 plus 2z cube plus 2z square plus z plus 1. So if you apply in the root table, that is 5, 2 and 1 in the Z5 row, and Z4 row is 3, 2, 1. If we need to calculate the values for Z cube, Z square, Z1 and Z naught. There are two sign changes in the first column. Hence there are two roots of the characteristic equation in the right half of S-plane, that is sign change from S4 z to the power of 4 to z to the power of 3 and z to the power of 3 to z to the power of 2. So the system is unstable. So we'll come for the second case. All the elements of any row of the root array are 0. This condition indicates that there are symmetrically located roots in the S-plane, which may be pair of real roots with opposite sign, pair of conjugate roots on the imaginary axis, complex conjugate roots forming quadrates. Polynomial whose coefficient or the elements above the rows of zeros are called auxiliary equation. Order of the auxiliary equation is always even. To proceed with the root table, replace the rows of zeros with the coefficients of polynomial obtained by taking first derivative of the auxiliary polynomial. So we'll take an example for this. So given expression is 10 divided by s to the power of 5 plus 7s4 plus 6s cube plus 42s square plus 8s plus 56. So s to the power of 5 is 168, s to the power of 4 is 7, 42 and 56. So if we take 7 in common in s to the power of 4, we'll get 168. So s to the power of 3 will get it as both the values 0, 0. So now I'll take the polynomial of f to the power of 4 as s to the power of 4 line as a of s is equal to x square plus 6s plus 8. So differentiating that equation with respect to s will get 2s plus 6. So in s3 column we have to write the value as 2 and 6. Then continue the calculation. All the element in the first column of the root array are positive. So the system is stable. This is condition 2, special case 2. So next, s to the power of cube 5 plus 2 s to the power of 4 plus 24s cube plus 48s square minus 25s minus 50. So 1, 24 and minus 25, 2, 48 and minus 50. So s cube row will be 0, 0. So we'll consider a of s is equal to 2 s to the power of 4 plus 48s square minus 50, and differentiating this equation with respect to s will get 8s square plus 96 s. So continue the calculation. So it is s square, s1 and s0. There is a single change of sign in the first column of the resulting array, that is s to the power of 1 to s0. Indicate to show the system is unstable. So there is one root with the positive real part. Solving the auxiliary equation 2 to the power of s to the power of 4 plus 48 s square minus 50 yields the roots as s square is equal to 1 and s square is equal to minus 25. So s is equal to plus or minus 1 and s is equal to plus or minus j 5. Determine the stability of the following characteristic equation. S6 is 1, 5, 8, 4. S to the power of 5 is 3, 9, 6. S to the power of 4 is 2, 6 and 4. S to the power of 3, if you calculate that, we will get it as 0, 0. So auxiliary equation will be 2s to the power of 4 plus 6s square plus 4. So differentiating with respect to ds, 8s cube plus 12s. So if we take the common as 4, I'll get it as 2 into s cube plus 3s is equal to 0. So continue the calculation. Solving the auxiliary equation, we have x square plus 1 into x square plus 2 is equal to 0, s is equal to plus or minus j1 and s is equal to plus or minus j root 2. There are two pairs of non-repeated roots on the imaginary axis. Hence the system is marginally stable. Using the root stability criterion, check whether the system represented by the following characteristic equation is stable or not. Determine the frequency of oscillations, if any. Characteristic equation is s to the power of 4 plus 2s cube plus 6x square plus 8s plus 8. So s to the power of 4 is 1, 6, 8 and s cube is 2 and 8. S square is 2, 8. So s to the power of 1 row will be 0, 0. So as is equal to 2s square plus 8 is equal to 0. Differentiating this with respect to s, 4s is equal to 0. So s to the power of value will get it as 4 and s naught value is 8. Solving the auxiliary equation, x square plus 4 is equal to 0. So s is equal to plus or minus j2. So the system oscillate with the frequency of omega is equal to 2 radians per second.